How's it going, everyone? My name is Mitch. I am an undergrad at the University of Utah studying computer science and applied math, and I do some cool compiler research under John Gear. So today I'm going to be talking about translation validation for LLVM's RISC-V backend. So for this tool we need a Live2. So just as a show of hands, I'm curious, who here has used a Live2? Decent amount. Okay, so a Live2 has a tool called LLVM, which formally validates refinements, and it's used for like middle end optimizations. And for those who didn't raise their hands, you can go and try it out at live2.llvm.org. So a Live2 verifies optimizations using Z3, and it's designed for middle end optimizations. So it looks something like this. We have some optimization, and we give the source IR and the target IR, and give it to a Live2, and it tells us whether the target is a refinement of the source. And we'll clarify what that means pretty soon. So before we talk about RISC-V-TV, we're going to first talk about the first tool, which was ARM-TV. So this can be thought of as happening in 4 steps. Step 1 is to just invoke LLVM's backend and generate some assembly. Step 2 is to lift the assembly back to IR and keeping it as a refinement. And then step 3 is to call opt to get a smaller IR to deal with so that a live can handle it. And then finally, step 4, we verify that the target is a refinement of the source. And what this means is, or the goal is to show that each of these steps, 1, 2, and 3, were all refinements of the previous. And if we get an error, if a live says that this translation did not validate, then that means that one of these steps was not a refinement, because refinement composes. So where I come in here is with RISC-V-TV, and RISC-V-TV is mostly the same thing. The main difference is going to be in the lifter. So there's a couple of reasons why the lifter is a little bit easier for RISC-V. First of all, the main reason is that there's no flags, so we don't have to deal with state, and we don't have to deal with undoing flag computations like we have to with ARM. So let's talk about how the lifter works. So the first step is going to be allocating storage for the registers, and then we allocate a stack and emulate the ABI. And the reason we're doing all this is to basically emulate a execution environment for a RISC-V function. So once we have this emulation, then we can translate each instruction into LLVM IR. And the way we do that is we load from our emulated register file that we have on memory, we get the arguments, and then we do some operation on them with semantically equivalent IR. And then we store the results back in the destination registers. So here's an example of the internals of the lifter. So what we're just doing is we're getting the operands from the registers, and then using an add operation from LLVM. And the reason this is so simple is because we're lucky in this case that LLVM's add function has similar semantics, or exactly the same semantics as the RISC-V add instruction. But this doesn't always happen. So sometimes there's some edge case, like maybe it handles one specific input differently, and we have to do some trick. Or in the case of some instructions, there's just no LLVM equivalent, and we have to fully flesh out the semantics of it. And one thing to keep in mind in these cases is that if we're implementing some instruction like this, and we need several LLVM instructions, then we want to do this in a way that is solver friendly, not necessarily performant or something else. So you could implement this with a loop or with some vector operation, but it turns out it's best in our case to just string together some bit manipulation operations so that Alive can more easily prove the translation. So after all that, we get a bunch of lifted code, and this looks like a lot, but most of it, the stuff in yellow, is just like register allocation, or by register allocation I mean storing the registers in memory and allocating a stack and some other spurious empty basic blocks. So if we trim all that down, what we're left with is a nice mapping here. And we can kind of think of this final target function we have here as having a prologue where we're doing all of the register allocation. Here's an example of emulating a register in memory. And then we can see by the highlighting that each instruction has its own basic block where it loads in its arguments, does whatever it needs to do, and then stores the result back in the destination register. And then that's kind of the body, and then we have the epilogue for the ABI on the return instruction, basically enforcing bit widths or sign extension or zero extension, whatever it needs to do. So once we have this whole system, then we need to start feeding tests into it to look for bugs. So where do we get tests? Well, one place is LLVM's test suite, and this basically contains a lot of the tests. Basically, it's designed to be testing what we're testing. So, of course, it's going to contain the patterns we want. We also use YARPGen. So YARPGen generates random C functions, and then we compile it to IR and use it as an input. Then we have Alive Mutate made by UUFine, and it creates slight variations of existing IR. So it could be inserting some instruction, or inserting some argument, or changing a bit width, something like this. Then we also use this kind of mouthful name of a project, LLVM mutation-based fuzz service. And this has another good mutator. It's made by Yingwei Zhang, who has helped us a lot with this stuff. So let's talk about an example. Here's some IR where we have a count trailing zeros being called, and that second flag just determines whether an input of 0 returns poison. So what this pattern is doing is saying if the input is 0, then return 0, else return the number of trailing zeros. And in RISC-V, the count trailing zeros instruction does not behave this way. So it returns just the bit width in the case that we have an input of 0. So if we look at the assembly now, we have this OR with 256, which is setting a sentinel bit, so that if we do call count trailing zeros, we get the bit width out of it. But then there's this AND instruction here that is masking off the high bit, the 8th bit, sorry, not the 8th bit, the 4th bit, which just is handling the case where we get an answer of 8. And so we get this select thing kind of cleverly handled within this single AND instruction. So Alive Mutate took this function and said, what if we had an I7? And then the problem may or may not be apparent now, where we have a problematic mask. So this mask is 6, binary 0, 1, 1, 0, and now half of inputs are wrong. So it appears that the way that this mask is computed is by just subtracting 1 from the bit width, and that doesn't work in this case. So we realized we can't do this optimization, this folding, in the backend with non-powers of 2. So I made a PR, and now we have some different code gen, but now it's correct. So what are the results from doing all this testing? Well, with ARMTV was a big project. It had a bunch of people involved, and paper just got published. And we found 45 previously unknown miscompilations in the AR64 backend. What about RISC-V-TV? Well, we found just one miscompile that's specific to RISC-V. So that's pretty interesting, but it's a little misleading because we also detected some unfixed bugs found by ARMTV, and we're just kind of trying to avoid double counting here. So why so few? Why are there so few bugs in the RISC-V backend? Well, it could be that because of the nature of backends and the amount of shared code, ARMTV may have found a lot of these low-hanging fruit and easier to find bugs. And it could also be that a lot of these bugs were fixed by folks like Craig Topper. So, thank you. So we learned that by fuzzing one backend, we got the benefit of fuzzing many backends or all backends because of the amount of shared code here. So not only are we finding less bugs because they're getting fixed and detected by previous fuzzing attempts, but it's also becoming easier to make the translation validator. So you get the benefit of doing this on a backend for all backends. And that's all I have for you today. Thank you.
Thank you so much, Mitch. Got a few minutes for questions. Any questions?
Over here. Great. Come on, let.
Great talk, and thanks for working on this. I think this is like a really interesting area. And yeah, I'm also really surprised to see that it was just that one bug that was found. I'm kind of skeptical almost because I know there's a lot of handwritten code in the RISC-V selection diagramming process. I'm curious, were there any particular RISC-V architectures or profiles or extensions that you were looking at whenever you were drifting? And if this might be part of the reason as to why we didn't find anything so far?
Yeah, so great question. We chose to use a very specific set of extensions here. It was just like bit manipulation, some floating point extensions, and these are just what we were told are kind of the common extensions to use. So one question might be, have you tested every combination of the extensions or something like that? And that could be something useful to do. It's not really clear. We also didn't test the RISC-V vector extension, which double or triples the size of the ISA, I think. So this is probably a place where we could find bugs. And the reason we didn't do that is because Alive doesn't support these scalable vectors. So,
Thanks.
Great talk. I'm curious about how to, if somebody's interested in using this, how much of this infrastructure is already upstream? Is there a way to kind of trigger this fuzzing tasks right from the upstream LLVM, or is it part of a different code base and you kind of point LLVM?
This lives in its own repo. None of this is really upstream. So a lot of the work is just the lifter that's specific to this project. We also don't have a way to do this from LLVM, if that's what you're asking. Yeah. Does that answer your question?
Yes, thank you. And one more question, it's kind of an extension to this question. Is there anything in the approach that prevents you from finding deeper miscompilation bugs? Once again, it's a question about do you have any plans about extending your analysis to find other families of bugs, or?
Yeah, we're not really sure what classes of bugs we're not finding. There's some interesting ideas, it's possible that we can undo a bug in lifting. That's annoying, and I don't want to speculate about how likely that is to happen or anything like that. But going forward, one thing we might do is, first of all, be able to support more extensions and test more of the backend. And another thing we could do is improve our fuzzing. So right now we don't know if our fuzzing is sufficient, and we could just need better mutations, more mutations, something like that.
Any other questions?
Yeah, I was curious if RISC-V maybe just overcounting. I was wondering if you tried anything with like LLVM, where you don't need a lifter, you just have LLVM bit code to start, or if you're sure like it's happening instruction selection or register allocation for the RISC-V stuff. Could explain why you're seeing so much fewer for RISC-V.
It's not totally clear. I didn't really talk about it much because we don't really know. It's a little hard to track what bugs were fixed, what bugs were existing in both backends. We'd have to go back and kind of just look at PRs and what people are talking about. So talk to me after, but I don't want to speculate too hard about why it's so low.
All right, let's give Mitch another round of applause, please.